In part 13 of this series, I focused on the gravimetric factor in regards to calculating the mass, that is, grams of an element or compound. Before any discussion on titration, an understanding of the term equilibrium is important. In this presentation, equilibrium is the starting point for the discussion of titration. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Consider this representation of a balance beam scale. Each pan is empty, and the beam is calibrated to be perfectly balanced. If some form of weight is added to the pan on the left, the beam would tilt downwards towards the left side of the scale. And by adding more weight onto the right side pan, having a mass weight that is greater than the weight on the left pan, the balance beam would tilt downwards towards the right side of the scale. Now, by adding additional weight to the left pan to be equal in mass weight with the pan on the right, the beam would return to its original balanced position. Now, this is the concept behind equilibrium. Consider now the equilibrium of ions in a solution. Using silver nitrate as our example is a reactant sample that will be analyzed. But for now, for this discussion, it is ions in solution and there is no reaction. The scale shifts to the left. As sodium chloride in solid form is slowly added in accordance with the solubility rules of common ions in water, the salt will dissolve and start to dissociate into individual ions. The chlorine ions start to combine with the silver ions, forming silver chloride ions in the solution. These become microscopic particles of precipitate floating around in the solution. These are nuclei. As the number of chlorine atoms equal the number of silver atoms, the scale starts to move to the right. When the number of silver nitrate ions becomes equal to the number of silver chloride ions, the scale will balance out. This is equilibrium. As soon as more chlorine atoms dissociate, all remaining silver will combine with the chlorine and the scale moves to the product side, the right side. A precipitate will form. If additional silver is added to the solution, the scale will start to move back towards the reactant side until the number of silver nitrate ions becomes equal to the number of silver chloride ions. The scale once again will become balanced or brought back into equilibrium. Here is another way of looking at equilibrium. As the illustration shows, there are cars moving in both directions across that bridge. These cars represent ions moving back and forth in a solution, that is, dissociating and recombining continuously. Each of the ion complexes reacting to form products and reactants. For every ion reacting to form a product, an ion will be reacting to form a reactant. This will continuously happen until the common ion exceeds the reacting silver ions in the solution to form a precipitate, or a reactant in the solution. The common ion can either be the chlorine, or it could be the nitrate. This is the common ion effect. A precipitate will form when the solution is oversaturated with the common ion. The equilibrium reaction equation is as shown, where A and B produces C and D and vice versa. A forward reaction is the reaction that forms the product, and a reverse reaction forms the reactants. The reaction rate in one direction equals the reaction rate in the other. Both forward and reverse reactions occur at the same time and at the same rate. The capital A and capital B represents the reactants, where the capital C and capital D represents the products. The lowercase letters represent coefficients of the reactants and products, used for balancing the equation. The double-ended arrow represents a forward and reverse reaction rate or equivalence. This equation, when rearranged, gives us a constant value. The letter K, capitalized, refers to the constant value. EQ stands for equivalence. The brackets represent the number of moles for the reactants and products. The products divided by the reactants gives us a constant for equilibrium. Coming back to the equation for the equilibrium constant, KEQ is given at specific temperatures. Therefore, it can change at different temperatures. Any change in the concentration of the reactant or the product will upset the equilibrium. Any shift in the equilibrium will force the reaction system back into equilibrium. However, any change in the product, now this could be C in the equation, will shift the system to the left, the reaction side. This in turn will reduce the concentration of D. A and B will increase in concentration. For the intended reaction, that is the reaction that is wanted to occur, the reaction system must be stable. This can be achieved by using or introducing a pH buffer solution, which will set up a buffer equilibrium. This stabilizes the intended reaction. Buffers are weak acids or bases, including their salts. Buffers resist pH changes in a solution if additional acid or bases are introduced. More on this later in the series. Now there are four specific or specified equilibrium constants. The first is Ka, which is the constant for a weak acid ionization. Kb is the constant for a weak base ionization. The A and B just distinguishes between the acid and the base. Kw is the ion product for water, which is an important constant, which is equal to 1.0 times 10 to the minus 14. Ksp is also very important as a constant. It is the solubility product constant. When discussing solutions, the solubility of a substance refers to the amount of the substance that can be dissolved in a solution before any residue or precipitate is formed. Then there is separation, which refers to the ability to separate one species from another, as was shown in parts 1 through 4 of this series. Any ions in a reacting reagent must be of sufficient concentration to exceed the solubility constant, Ksp. Now Ksp is the constant that is used for the calculation of the solubility of a solute or the concentration of ions in a solution when there are no excess of either ion present. This would be the state of equilibrium. This constant is also used to predict the conditions for which a precipitate may form, or predict the conditions of which a solid may dissolve. The lower the Ksp value is, the less soluble the species is. More on this later. In order to calculate the Ksp value of a species, the solubility in grams per liter will need to be known. Now there are tables that will give the values for the solubility of compounds. Many values are contradictory. The values in these tables are based on the calculations involving temperature as well as atmospheric pressures. There were also discrepancies in the accuracy of the measuring equipment. However, most of the values in these tables are pretty close to being somewhat accurate and precise, and thus may be used. The first example asks for the solubility constant for silver chloride. Well, if silver chloride was to dissociate in a solution of water, there would be 1 mole of silver ions and 1 mole of chlorine ions. The ratio between the compound and each ion is 1 mole of the silver chloride to 1 mole of the silver ion to 1 mole of the chlorine ion. The ratio is therefore 1 to 1 for each of the ions in respect to the compound. The KSB value is equal to the number of moles of silver multiplied by the number of moles of chlorine divided by the number of moles of silver chloride. Now, in the solubility table that I used for the calculations, it states that 1.435 milligrams of silver chloride will dissolve in 1 liter of water. Now, dividing the 1.435 milligrams per liter by the mass molecular weight of 143.4 grams per mole of silver chloride, the moles per liter equates to 1.007 times 10 to the minus 5 moles per liter. The KSP value is therefore 1.007 times 10 to the minus 5 multiplied by 1.007 times 10 to the minus 5 moles divided by the 1 mole of the silver chloride. The solubility constant is equal to 1.014 times 10 to the minus 10th. In this example, the KSP is calculated using the same formula as in the previous slide, but requires balancing. It must be also remembered that a mole is a representation of anything. It is a concept. Silver chromate has the formula of Ag2CrO4. This molecule is actually comprised of 2 molecules and a metallic element. The silver chromate, as shown, this formula can be written in 2 ways. One formula incorporates the use of parentheses containing the chromate ion. The chromate ion is considered as a single ion, a polyatomic ion, that contains a metallic atom, which is a positive cation, and a non-metallic atom, which is a negative anion, covalently bonded, thus considered as just a single ion. The ratios between the silver chromate, the silver ion, and the chromate ion is 1 to 2 to 1. As there are 2 atoms of silver in the formula and only 1 polyatomic chromate ion, the KSP equation is therefore slightly changed as shown. The silver chromate solubility is 0.028 grams per liter and has a molecular weight of 331.8 grams per mole. The moles per liter still needs to be calculated and is the same as the previous slide. The 0.0287 grams per liter is divided by the molecular weight of the silver chloride, which equates to 8.650 times 10 to the minus 5 moles per liter. The ratio between the moles of silver chloride and the silver cation is 1 to 2. As there is 2 atoms of silver in the silver chloride formula. The mole can represent any item, and therefore in this context, 1 mole of silver equals 2 atoms of silver. This balances the KSP equation. KSP is then equal to 2 moles of silver multiplied by 1 mole of chromate divided by 1 mole of silver chloride. Since the mole of chromate is equal to 1 mole of silver chromate, we can now plug in the numbers. Now 2 atoms of silver equals 2 times 8.650 times 10 to the minus 5 squared. This is then multiplied by the 1 mole of chromate, which is 8.650 times 10 to the minus 5, and then divided by the mole of silver chloride. This gives us a KSP value of 2.59 times 10 to the minus 12. In this example, the question is, what is the product KSP for the fluorine ion when the solution contains 0.0078 grams per liter of calcium fluoride? As shown, the dissociation of the calcium fluoride molecule results in 1 atom of calcium and 2 atoms of fluorine. The ratio is thus 1 to 1 to 2, meaning a 1 to 2 ratio in respect to the calcium fluoride compound. The mass weight of the calcium fluoride is 78.1 grams per mole, and the fluorine atomic weight is 19.0 grams per mole. Since this is a saturated solution of fluorine ions, the solubility of the fluorine at 25 degrees centigrade must also be 0.0078 grams per liter. Therefore, the moles per liter of fluorine is 0.0078 divided by the atomic weight of 19.0 grams per mole of fluorine. This equates to 4.105 times 10 to the minus 4 moles per liter, or 4.105 E minus 4 moles per liter. Now the reaction equation shows that there are 2 atoms of fluorine and 1 atom of calcium. The calcium is 1/2 of the fluorine as the ratio is 1 to 2. The KSP is thus equal to 0.5 times 4.105 E minus 4. The value here is then multiplied by the 4.105 E minus 4 squared because of the 2 moles of fluorine. This equates to a value of 3.46 times 10 to the minus 11 for the KSP value of the fluorine. This snippet of a KSP table is one of many solubility product constant tables which should contain notes about the parameters of which the values were calculated. That is, the measurements taken in relation to the temperature given, the amount of compounds in grams used for the experiments, and the volume of solvents used. I recommend searching for and downloading a good copy of these tables, as not one table shows all compounds and the KSP values. Now this table will be needed going forward. The ICE table is a valuable tool to use for the calculation of the number of moles of a substance in a solution. The acronym ICE stands for Initial, Change, and Equilibrium. Now, at the start of any dissociation of a compound, there are no ions present in the solution. As soon as the compound starts to dissolve, there is a change that is happening, and when the reaction is completed, there will be a number of ions in the solution as well as some compound that is not dissolved due to the back and forth reaction happening simultaneously at equilibrium. Now, during the change period within the dissociation reaction, ions are separating from the compound, and at the end of dissolvement, the number of ions would be fully dissociated from the compound. The compound and the individual ions are typically represented with an X. Now, at the beginning, there was 0 ions, that is, individual ions present. Then there is this change, which is represented by the X minus. The dissociated ions are represented as X plus. At equivalence, there will be a total number of individual ions in solution. The amount of compound still in solution at equivalence would be next to nothing. The amount should be extremely minute at equilibrium, and therefore can be ignored or considered as 0, or considered as completely dissociated. However, this amount can be calculated using a quadratic equation, but not necessary for most of these determinations. For this example, using lead orthophosphate, the question always comes up: how much solute is required to saturate a solution at equilibrium without having any residue? Well, the formula for the lead orthophosphate is shown. The KSP table listed the orthophosphate as having a KSP of 1.0 times 10 to the minus 32nd. The ICE table in the dissociation equation shows that there will be 3 moles of lead and 2 moles of phosphate in the solution at equilibrium. Therefore, how much of the phosphate do I need to dissolve for a saturated solution? Based on the 3 atoms or moles of lead-2 and 2 atoms or moles of phosphate, mathematically it can be represented as 3x for the lead and 2x for the phosphate, 1 mole for the lead orthophosphate. The KSP value from the KSP table shows the lead orthophosphate has a KSP value of 1.0 times 10 to the minus 32. The numbers from the reaction equation and the ice table can now be entered into the equation as shown. Now take note, the remaining moles of lead orthophosphate at equilibrium would be extremely small, and therefore the 1 minus x can be considered as 1 mole. Therefore, the equation is simplified as 1 times 10 to the minus 32 equaling 3x cubed multiplied by the 2x squared. Well, the 3x to the third multiplied by the 2x to the second can be further simplified. This changes the equation to 1.0 times 10 to the minus 32 equaling 27x to the third multiplied by 4x to the second. The 27 is derived by the exponent. Therefore, 3 times 3 times 3 equals 27, or 27 to the third. Same for the 4x to the second, which equals 2 times 2. Well, the 27x to the third multiplied by the 4x to the second can be further simplified by adding the exponents together. The equation can then be written as 27 times 4 to the 3 plus 2, which equals to 108x to the fifth. This simplifies the equation even further as the equation becomes 1.0 times 10 to the minus 32 equaling 108x to the fifth. The 108x to the fifth is further simplified by dividing by 108 as shown. Through the process of elimination, the 108x fifth divided by 108 gives us 8 to the fifth, or that is x to the fifth. The full equation is now x to the fifth, which equals 1.0 times 10 to the minus 32nd, which has to be divided by 108. This leaves us with 9.26 times 10 to the minus 35. Well, this equation is then further simplified by canceling the exponent in the x to the fifth by square rooting the x to the fifth and the 9.26 times 10 to the minus 35. This leaves us with just x, and x is equal to 1.56 times 10 to the minus 7 moles per liter. Now the lead orthophosphate has an atomic weight of 811.6 grams per mole. Therefore, the 1.56 times 10 to the minus 7 moles per liter multiplied by the 811.6 grams per mole equates to 1.274 grams per liter of orthophosphate. Therefore, the final answer would be 1.27 times 10 to the minus 4 grams of lead orthophosphate would dissolve in 1 liter of solution. There are times that one will need to know what the pH value of a solution would be. In this series on classical assay, it has been noted that precipitation can be affected by the pH balance of a solution. Now, using magnesium hydroxide for this example, what will the pH of the solution be? Well, magnesium hydroxide consists of 1 atom or ion of magnesium and 2 ions of the polyatomic molecule hydroxide. From the KSP table, magnesium hydroxide has a KSP value of 5.61 times 10 to the minus 12. Since 5.61 times 10 to the minus 12 is equal to 1 mole of magnesium and 2 moles of hydroxide, the formula can be simplified by stating that 5.61 times 10 to the minus 12 is equal to 4x cubed, as shown. Now, dividing 4x cubed and 5.61 times 10 to the minus 12 by 4, algebraically we end up with x cubed, which equates to 1.40 times 10 to the minus 12. Cube rooting the x cubed as well as the 1.40 times 10 to the minus 12, we end up with just x, and x equals 1.12 times 10 to the minus 4 moles per liter. Now, since x represents 1 mole as being just 1x, the number of moles of magnesium equates to 1 mole per liter. However, there are 2 moles, that is 2x of hydroxide. The moles of hydroxide is 2 times that of magnesium. That'll be 2 times 1.12 times 10 to the minus 4 moles per liter, which equates to 2.24 times 10 to the minus 4 moles per liter of hydroxide. Now, POH is equal to the antilog of the moles of hydroxide. Therefore, POH equals the minus log of 2.24 times 10 to the 4th moles of hydroxide. pH plus POH is equal to 14. The pH scale goes from 0 to 14, but in some textbooks it'll state 1 to 14. The antilog of 2.24 times 10 to the minus 4 equals or equates to a POH value of 3.65. Therefore, 14 minus the 3.65 gives us a pH value of 10.35. Now, as a side note for information, a pH greater than 10 will inhibit the formation of the deadly cyanide gas, hydrogen cyanide, from a cyanide gold leaching solution. In this example, where sodium chloride is added to create a solution containing silver chloride, what will the effect be? The reaction equation is shown. Note that the product will dissociate until all of the silver ions are equal to the number of chlorine ions in the solution at equilibrium. Therefore, the KSP value is based on the silver chloride. As was mentioned in a previous presentation, an overly excess amount of chlorine will form a soluble silver chloride. Well, in this presentation, I want to show the difference in silver ion concentration when 0.001 moles of sodium chloride is added to create the solution, compared to the solution having added sodium chloride to bring the chloride solution up to 0.01 moles of chlorine. Having the KSP value from a KSP table of 1.6 times 10 to the minus 10, and the ratio being 1 to 1 in terms of the silver ions and chlorine ions in the silver chloride solution, the moles per liter, as shown, is 1.26 times 10 to the minus 5 moles per liter for each element. 1.26 times 10 to the minus 5 moles of silver multiplied by the 1.26 times 10 to the minus 5 moles of chlorine equals the KSP value of 1.6 times 10 to the minus 10. Okay, the moles of silver, therefore, at 0.001 moles of sodium chloride is equal to the KSP value of 1.6 times 10 to the minus 10 divided by the molar concentration of the chlorine in the sodium chloride solution. This equates to 1.6 times 10 to the minus 7 moles per liter. Since the KSP value of the number of moles per silver multiplied by the number of moles per chlorine, the new KSP value is equal to 2.56 times 10 to the minus 14. Adding more sodium chloride solution to bring the chlorine molar concentration to 0.01 moles, the concentration decreases to 1.6 times 10 to the minus 8 moles per liter as shown. The new KSP value also decreases to 2.56 times 10 to the minus 16. It should be noted that the KSP value decreases. The solubility of the element, in this case the silver, also decreases. Precipitation should increase. This is the common ion effect. Therefore, the precipitation of a compound can be determined by the comparison of the KSP values. The increasing KSP value indicates that a compound is more soluble when compared to the KSP value of a different compound, when there is more than one metallic ion existing in the solution. It must also be noted that a complex ion may form when there is an excess of the common ion. Now, an excess of chlorine in the presence of silver may form the complex silver dichloride molecule, which is soluble. There is another constant which is not shown. This constant is Kf. It is the compound formation constant. The formula is K, which is equal to Kf divided by Ksp. The equation for the K constant was shown earlier in slide 5 of this presentation, where the Keq is equal to K, which was equal to the moles of product divided by the moles of reactant. In this example, it is a small study between dissolving silver chromate using two solutions, silver nitrate and potassium chromate. To start, what is the solubility of silver chromate in water? Well, the Ksp value for silver chromate from a Ksp table is 1.12 times 10 to the minus 12. The chromate compound associates, as shown, having two silver ions and one chromate ion. The equation is 1.12 times 10 to the minus 12, which is equal to the 2x squared multiplied by 1x, then divided by the 1 mole of the silver chromate. Now, the remaining amount of silver chromate that's remaining in solution at equilibrium is so small that the mole can be considered as 1 mole. The equation is then algebraically simplified as shown. The amount of silver chromate that should dissolve using the Ksp from the table is 6.54 times 10 to the minus 5 moles per liter, or 0.0216 grams of silver chromate per liter. Dissolving a silver chromate in a 0.001 molar solution of silver nitrate, the solubility is equal to the Ksp value of 1.12 times 10 to the minus 12, divided by the 0.001 squared, which gives us a value of 1.12 times 10 to the minus 6 moles per liter, or 3.72 times 10 to the minus 4 grams per liter. At a 0.01 molar solution, the solubility becomes 1.12 times 10 to the minus 8 moles per liter, or 3.712 times 10 to the minus 6 grams per liter. As there are two silver ions in the formula, the molar amount of the silver concentration had to be squared. The equation became Ksp divided by the 0.001 squared. Also note that the common ion is silver, as we were adding silver chromate solid to a solution of silver nitrate. In the second part, the concentration of the solution will be the same. However, the solution used is potassium chromate. Now, since there's only one chromate in the formula, the ratio is 1 to 1. The number of moles of silver is squared, as there are two ions of silver in the formula. The solubility, therefore, becomes Ksp divided by 0.001. Now, this equates to 1.12 times 10 to the minus 9. To calculate the number of moles of silver, the 1.12 times 10 to the minus 9 had to be square rooted, giving the value of 3.35 times 10 to the minus 5 moles per liter of silver, or 3.61 times 10 to the third grams per liter of silver. Now, in the second part, having a 0.01 solution, the moles of silver is calculated as 1.06 times 10 to the minus 5, or 1.13 times 10 to the third grams per liter. Note that the common ion in the solution is the chromate. The potassium, being a group 1 element, will remain soluble in the solution. The takeaway here is that the Ksp value can be used to determine the molar concentration of an element in solutions of different molarities per liter. The theory of gases is quite complex. However, I need to discuss in general the concept of the ionization of gas in water. The picture on the left is a representation of an experiment where the addition of carbon dioxide gas is allowed to bubble through some distilled water. The synthesis of this reaction forms a weak carbonic acid solution. In reference to hydrogen sulfide gas, there are two distinct reactions that occur. The first is the hydrogen sulfide dissociates into hydrogen ions and hydrogen monosulfide ions. The second reaction is the hydrogen monosulfide ions dissociating into hydrogen ions and sulfur ions. Now from the Ka tables, the first reaction has a Ka value of 8.9 times 10 to the minus 8. The second reaction has a Ka value of 1.0 times 10 to the minus 19. H2S in water forms a weak sulfuric acid solution. Now, as there are two reactions that take place, the final constant K is determined by multiplying both Ka values as shown. The Kasp value for the overall H2S is 8.9 times 10 to the minus 27. In a 0.1 molar saturated solution of H2S, 8.9 times 10 to the minus 27 multiplied by 0.1 equates to 8.9 times 10 to the minus 28 moles per liter. Now the sulfur concentration therefore is equal to the 8.9 times 10 to the minus 28 divided by the 0.1 squared, which gives a value of 8.9 times 10 to the minus 26 moles per liter, or 2.86 times 10 to the minus 24 grams per liter of sulfur. In parts 1 through 4 of this series, the separation of elements into groups was the focus. To separate the group 2 elements consisting of arsenic, bismuth, cadmium, copper, mercury, lead, antimony, and tin, and the group 4 elements consisting of cobalt, manganese, nickel, and zinc, hydrogen sulfide gas was used. For the group 4 elements, ammonium hydroxide was used to increase the pH value of the solution, allowing for the group 4 elements to precipitate. Now, in the previous slide, the solubility of the hydrogen sulfide gas was discussed. To bring this all together, an example using a 0.20 molar solution of hydrochloric acid containing 0.1 moles of copper and 0.1 moles of zinc is used. Now, from the previous slide, it was shown that the Ksp value of a 0.1 molar saturated solution of hydrogen sulfide gas is 8.9 times 10 to the minus 28. Therefore, the number of moles of sulfur is 8.9 times 10 to the minus 28 divided by the 0.20 molar solution of hydrochloric acid gives a sulfur content of 4.45 times 10 to the minus 27 moles. The equation for AQ value is the same as the equation for Ksp, which was discussed previously in the series on classical assay. Now the Q value for the copper is 0.01 moles of the copper multiplied by the 4.45 times 10 to the minus 27 moles of sulfur, which gives a Q value of 4.45 times 10 to the minus 25. Well, the Ksp value listed in the table for copper 2 sulfide is 6.0 times 10 to the minus 37. Since Q is greater than Ksp, that is, the solubility product of the copper compound has been exceeded and will form a precipitate. Since there is also 0.01 moles of zinc in the solution and 4.45 times 10 to the minus 27 moles of sulfur, the Q value is the same as the copper sulfide. However, the Ksp value for the zinc sulfide is 2.0 times 10 to the minus 25th. Now Q is also greater than Ksp and a precipitate should also form. However, the Ksp for the copper sulfide is smaller than the Ksp for the zinc sulfide. The copper is far less soluble than the zinc and will precipitate first, leaving the zinc in solution as a zinc chloride. By adding hydroxide increases the basicity, that is the pH value of the solution. This weakens the chloride solution, that is, it neutralizes the hydrochloric acid, and allows the additional sulfur from the added hydrogen sulfide gas to react with the zinc, which in turn forms an insoluble zinc sulfide. In a previous slide, I mentioned that precipitation can be controlled by using a hydroxide. Now to start, one must have some understanding of the properties surrounding hydroxides, especially ammonium hydroxide. Ammonium hydroxide is synthesized by adding ammonia, which is a nitrogen trihydrogen gas dissolved in water. The end product is an ammonium hydroxide solution. An ammonium solution is basic in regards to an acidic or basic solution. Therefore, the equilibrium constant is labeled as Kb, the equilibrium constant for bases. The constant listed in the Kb table for ammonia is 1.8 times 10 to the minus 8. The precipitation of a species can be controlled by the amount of hydroxide there is in the solution. The hydroxide itself is controlled by the molar amount of ammonium there is in a solution. Therefore, additional ammonium can be added by the introduction of ammonium chloride to a solution of ammonium hydroxide. Case in point, if we have a 0.20 molar ammonium solution containing 5 grams of ammonium chloride per 100 milliliters and a molarity of 0.10 moles of zinc, will the zinc hydroxide precipitate? Now keep in mind that the product of an ammonium solution is ammonium hydroxide. Also, zinc is soluble in a chloride solution. The question then becomes, will there be enough hydroxide to exceed the solubility coefficient of the zinc hydroxide? The amount of hydroxide required in the solution can be determined. The KSP from the KSP table shows that the KSP for zinc hydroxide is 1.2 times 10 to the minus 17. Now there are 2 hydroxide ions in the formula. Since there are 0.10 moles of zinc, the formula can be rearranged as shown. Because there are 2 moles of hydroxide, for the actual amount that is required equals to the KSP value divided by the 0.10 moles of the zinc, then square rooted. This equates to 1.1 times 10 to the minus 8 moles required for the precipitation to occur. The concentration of ammonium determines the amount of hydroxide in a solution. By adding the ammonium chloride, as stated, the amount of ammonium needs to be determined. The dissociation of the ammonium chloride is 1 mole of ammonium ion to 1 mole of chlorine ion, a ratio of 1 to 1. Since there are 5 grams of ammonium chloride per 100 mils dissolved in the solution and 1 mole of ammonium chloride, which has an atomic mass weight of 53.5 grams per mole, and there is 1,000 milliliters per liter. As shown, the molarity is 0.93 moles of ammonium. The actual amount of hydroxide can now be determined as shown. The 0.20 molar solution is multiplied by the KSP value of the ammonia solution, then divided by the molarity value of the ammonium ion. We get a molarity value of 3.87 times 10 to the minus 5 moles. Comparing the required amount of hydroxide with the actual amount of hydroxide, there is more than enough hydroxide ion in the solution to effectively precipitate the zinc hydroxide compound. Well, this concludes part 14 of this series on classical chemical assay for small-scale miners, prospectors, and hobbyists. In this part, equilibrium was the topic and focus. It is the beginning of the discussion on titration. I tried to show the examples in a way that anyone without a chemistry background could understand, and I hope that I was successful in this goal. It was shown not only on calculating the weight of a species within a sample, but by using equilibrium to predict the separation of elements within a sample as well. I hope that the information presented in this presentation was informative, and that it may entice you to view part 15 when it is published. If you found this presentation not so boring and informative, or if you know of someone that may benefit from this presentation, please give it a like and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.